Okay, I did finally get Lab 2 grade. I sincerely apologize. I mean, what good is it to get it graded 60 days late? Yes, at least that's what it told me. And I really apologize, especially there were a lot of things. I got the first one graded really quickly to make sure people would understand mistakes they made. But the second time through, 12 people, that's a significant fraction, only include the first part of the procedure. They only talked about the first little bit and skipped all the rest of the procedure. One person skipped the entire procedure. And then 3 people had no results section. 2 people had no conclusions. 2 had no equations. The equation there was just the one equation. Now, I did not take off for this on this one, but will in future ones like the one that's done today and later. A lot of people did not say V equals speed delta x equals change in position. I'm sorry, I'm just going to move this so I actually have room to write them out. So I didn't take off for that, but a lot of people forgot to put those things. With your equations, you need to define what they are. In this lab here, we didn't actually calculate with that equation. We let the computer do it, so you didn't have to show a sample calculation. If you had actually done the calculation, then you would have shown one example putting numbers into it. Leslie. Okay, 2 people skip conclusions. Yeah. The results, just a reminder, the results should be a succinct statement of the outcomes. So on that experiment, you did have, I wasn't really looking hard for this, but the result was, when you're going away, the slope is positive. We're going toward, the slope is negative. The faster you go, the steeper the slope. You did have those results. The one I was really looking for was the average velocity that you got from finding the slope of a line compared to the average of the velocity values. In the results, you should say, my hypothesis was confirmed or not, but that's all in the hypothesis. The rest of the hypothesis discussion should come in the conclusions. In the conclusions, you need to say what you learned, what went well, what could have gone better. A lot of people did really well in the conclusions. Things like, I learned what I was supposed to learn here. It would have worked better if we hadn't been using humans with their reaction time and their inconsistent, there was a lot of good thought there in the conclusions. A few people forgot to say if their hypothesis was confirmed or not, and if it was, what the reasons they have for coming to that conclusion, because you need to have that, your reasoning behind how your hypothesis turned out. So want to make sure I covered that, because hopefully, okay, so Jordan is grading the labs. I haven't checked to see if he got any graded over the weekend or not. But hopefully from the next lab on, we'll have definitely better reports where people don't forget to include things. There were a few that had a lot of mistakes, like didn't put titles that are meaningful. Remember, when you make a graph, the graph should have a meaningful title, like what should the person get out of this? A lot of people put things like position versus time. Well, that's a useless title. It doesn't help anyone anywhere, because you have to have position with its units on this axis and time with its units on this axis. If you already have those written down, putting your title, it's just redundant, right? There's no point in having it. It doesn't help you. The title should be something that a person looks at the graph and says, this is the point of the graph. Okay, this should be our last lecture on material that will be on the exam, originally scheduled for tomorrow, but postponed until a week from tomorrow. So tomorrow in lab, we'll be doing the temperature experiment that's scheduled for a week from tomorrow. Next week, we'll be doing the exam. Erica is dying to ask me a question.
So for the exam, are we just gonna stop here and just take this information from here?
I should, assuming I get to the end of my slides today, yes.
Okay, so we don't, like, all the new information we learned, that's not gonna be on the test.
Right.
Okay.
And unless I don't finish today's lecture, then it would go through the end of what was supposed to be today's lecture. Of course.
Also, you drop one lab.
No.
I mean, you think about it.
Sure, I'll think about it for a little longer than that quick reaction, but the answer is probably still going to be no. Okay. So today we're going to be learning about flowing fluids. Now, we ended last class by playing with fluids, and now this here, my blow dryer, doesn't have quite enough power to do cool things on this one. You can see that the water level rises a little when I blow over the top, but not a lot. Now, if I blow down, of course, it goes down. If I blow over this one, I can blow water out, get a little wetness out there. Why is it that it's able to blow some water out when I blow them across the top?
Lower pressure pulls it out.
Okay, it's lower pressure, but it doesn't pull it out. It's lower pressure on top. You have atmospheric pressure pushing down on the other ones. So that the atmospheric pressure then, you come down, the pressure goes higher as you go lower, pushes up here, and you have more pressure pushing up here because the atmospheric pressure outside than you have pushing down on the top. So what you said is what a lay person would usually say. They would usually say, you lower the pressure so it pulled it out. But lower pressure is still pushing in. The lower pressure on top was still pushing down, but it was pushing harder up, and thus the net force was upward and it came up. Now, this is one of my favorite demonstrations. I mean, I'm a physicist. I love demonstrations. So, ping pong ball, air stream. How many people have seen a demonstration like this? A few. So, is that cool or what? Yeah. Here's what I love. Magic, right? Now, what was, since you're going to, or somebody in some foreign country is going to watch this video, they couldn't see what I was doing there. So describe what was going on. What was so cool that makes me love that demonstration? Okay, the ball was floating. I had the blow dryer at an angle. And so air was coming out of the blow dryer like this. And then I had my ball hanging out up here. So when the ball was directly over the blow dryer, you're all, well, yeah, there's momentum in the air coming up. The air hits the ball, bounces back down. The change momentum for the air was downward. Hence, there was a net downward force in the air, which means there was a net upward force in the ball. You can explain it with Newton's second law, what's happening when the ball is directly above it. But when it's off to the side, it's not so simple. What forces are acting on the ball when it's off to the side like this? Okay, so we have force of gravity, which by definition is what direction? So we had a force of gravity pushing down. If it's stationary, it was relatively stationary. What do we know about the forces? Yes. If it's stationary, it's an equilibrium. Now, I forgot what I was grading yesterday, but it's something I had a number of people who said that when something has a velocity of zero, or when it has a straight line on a position versus time graph, that means the velocity is zero. No. Straight line on position versus time graph means the velocity is not changing, which is equilibrium. Equilibrium is constant velocity, but it doesn't have to be zero. But here it is zero, so it's an equilibrium. Thus, the sum of the forces is equal to zero. So if I have that downward force due to gravity, there has to be an upward force. Now let's think about what other forces could you come up with acting on the ball to make it levitate. What? Okay. Gila says the air. Now, the air is a little complicated, so I want to know what direction is the force from the air. Okay, it's station. Okay, the direction the air is blowing. Okay, so Gila is saying the one that I talked about that would explain why the ball just stays directly above the blow dryer when I'm pointing up, a force like this. And I'm going to put force due to change in momentum of air. Right, the air hits it, bounces off, equal and opposite force. There's a net force pushing up that direction. What else are you going to have? Okay, atmospheric pressure. Now, atmospheric pressure normally would be essentially the same, pointing in all directions. But now we have air flowing. So we have some air that's flowing over the top and some that's flowing over the bottom. And so some air is going like, and some air is going like this. Now, of course, gravity is going to make it fall a little. As it falls a little, the air that comes to the middle is going to be going up like this. And so you're going to have more air going over the top than under the bottom. A result is the pressure on the top is going to be lower than the pressure on the bottom. And so we're going to have the two final forces, force air top and force air bottom. The force air bottom is a bigger force because you have higher pressure on the bottom and lower pressure on the top because the air is going faster over the top than it is under the bottom. And so it's that difference in air speed over the ball that allows it to levitate. It's totally cool. Now there's other demonstrations. When we were in Washington, D.C., you guys were here, they had a demonstration that I really should fix up. It's so cool. You have a box with a hole in the top. And you put a blower that blows air down. And then you take a disc and you put a disc here. What do you suppose is going to happen? If there's no air, what's going to happen to that disc? It's going to fall because you'll have the downward force of gravity, upward and downward forces due to air pressure will balance and it just falls. But when you blow air in the direction shown, when you bring it up high enough, it will suck up and stay there. Yeah, I see quizzical looks. And I know I can't do the demonstration here, so you're like, hey, could be lying. What possible reason could there be for it to suck up and stay there? You have that, oops, wrong color. You have that air has to split up and go like this, and it has to go really fast to get out of that little area because you have the flow rate that's going down the big hole has to equal the flow rate that's coming out sideways, but with that small area, it has to go really fast. So if the air goes really fast, what happens to the air pressure on the parts over to the side? What's happening to the air pressure here and here? Really low. So you have atmospheric pressure pushing up here, a force due to atmospheric pressure. And then you have a force here that's the area of that littler portion times the pressure in there, which is going to be probably bigger than atmospheric pressure. But then you have a really small pressure. The small force is pushing down the sides, and the net force due to air is upward.
Would the speed of the air create a problem if it was too high? Like, would it just push it off?
I'm sure if you go too fast, that would occur. And obviously, if you go too slow, it would not have enough upward force. Since I don't have one, I've never been able to play with the different air speeds. But it's so not what you expect. Okay, by the way, we are going to talk about the difference in laminar flow and turbulent flow today, assuming I go quickly since I've already spent 15 minutes and haven't started. Laminar flow means layered flow. Water or a fluid flowing in layers, smooth flow. Turbulent flow, well, it's turbulent. You have lots of crazy action. You form little pockets of vacuum. Turbulent flow, you can hear a pipe when it has turbulent flow because of the random motion of the molecules hitting the walls. But we first have to finish a few things, some examples using the Bernoulli equation. So here's one example. I have a picture of a dam from Bulgaria. And we have a hole in the dam, an intentional hole, for water to flow out at the bottom. And instead of making it a hydroelectric dam, we like to make hydroelectric power. That is, we take the potential energy of water up here, and then we let it flow out here. It's converted that potential energy into kinetic energy. That kinetic energy then is used to do work on a turbine to slow it back down, and we create electricity that way. But this one here, we're just saying it flows out. And the question is, how fast does the water flow out of the dam? Now, what things do you think might affect how fast the water flows out of that dam? Go ahead, Eric. Okay, how full you said?
Yeah.
Okay, so the difference in the height of the water. Okay, the size of the opening. Any others? The what? Well, we're looking at what would affect it.
Well, like before.
Oh, okay, the velocity coming in. Okay, that is true. I'm going to stipulate that we have still water. Irving. Okay, Irving says the temperature. The temperature, every answer so far has been a good answer. Okay, we're going to ignore the answer that Amanda gave us because it's hard. The very last slide will address what that would do to affect us. The very last in today's lecture. It is very important, but it's one that we pretend doesn't exist. The temperature will make some difference. It'll make a difference in the density of the water, which of course then will affect the pressure. And also the kinetic theory of gases, it affects how fast the individual molecules are moving. But for the most part, we would say temperature probably isn't a consideration. So if we just use the Bernoulli equation and we ignore Amanda's answer, which was a correct answer, but we're ignoring it, then we only have three variables: pressure, height, and speed. And so a person might have said pressure, but here's the thing. The top of the dam is open to the atmosphere. So what's the pressure at the top of the dam? Atmospheric pressure. This hole here is open to the atmosphere. So when the water comes out of the hole, what's the pressure when it comes out of the hole? Atmospheric pressure. So the pressure is the same on top and bottom. That's why I said this here is this. It's Torricelli's theorem now. Torricelli's theorem is, hey, let's say, what if the pressure is the same on both ends? Then how does the speed change with height? Right? It's just taking Bernoulli's equation and taking a special case. So if we want to find the speed at which it comes out, all we have to do is take the Bernoulli equation, which I wrote here. Notice the red and the green are exactly the same, except for the subscript is 1 in red and 2 in green. And then we just solve for speed. So I stipulated that the speed of the water at the top is 0. So I'm just going to use the top there where I have the purple circle and find the relationship between V1 and V2. So taking that relationship, 1/2 rho 1 V1 squared minus 1/2 rho 2 V2 squared. So I just move those to the same side of the equation. Stupidly, I move them to the wrong side of the equation, but you know what? We can deal with that. Equals rho 2 GH2 minus rho 1 GH1 plus P2 minus P1. Now that is just rearranging the equation. So I have the velocity stuff on one side, the pressure stuff on the other. And you notice the 2 is negative on the left and positive on the right. The 1 is just the opposite. Now, given our situation here, P2 minus P1, what's the value there? The difference in pressure between the atmosphere here and here? Roughly 0. I say roughly 0 because you are at different elevation. Change in pressure is rho g delta h, but what's the density you're going to use to calculate the pressure difference from here to here in atmosphere? Be the density of air, and the density of air is quite small, and so we consider that negligible because of the small density of air. That reminds me, the rest of these terms have rho 1 or rho 2. When I worked this out on Friday, I only had rho. I didn't put rho 1 and rho 2. If I wanted to be technical, though, which I did today, I would put rho 1, which is the density of the water at the top of the dam. Rho 2, the density of the water when it comes out of the dam. For our approximation that fluids are non-compressible, rho 1 is equal to rho 2, which is why I did not put rho 1 and rho 2 on Friday. So we will go ahead and say, within the approximation that water is incompressible, I can then divide out the rhos. Since this here was 0, sure, I divided it by rho, but it's still 0. Finally, I'll just multiply everything by 2 and get so V1 squared minus V2 squared is equal to 2G H2 minus H1. We stipulated that V1 was 0, and so finally V2 is equal to the square root. And I'm going to change the order of the H's because of the sign change. And so the speed at which it comes out is square root of 2G times the difference in height. This equation should look familiar. This equation looks familiar because if I drop a ball, that's how fast the ball would be going after dropping a distance h1 minus h2. Is this falling straight down? No. Something no one said that I thought people were going to say that might affect the speed is the direction the water comes out. But this equation didn't have direction to it. Why? Because we used the work-energy relation to derive the Bernoulli equation. And since work-energy has no directionality to it, it doesn't matter what direction the water comes out. It could be shooting up, it could be shooting down. It could be shooting horizontally. It's still going to have the same speed. Now, a question on this. I said this is the same speed a ball would have had if you dropped it and it went down that height. If the nozzle was pointed straight up and there's no air resistance, how high would this stream of water go? It has the same speed that a ball would have if you had dropped it a height h. So we get down this height h below, and if we shot the ball straight up with that speed, how high would it go? It'd go back up to where it started. And so this water stream, if there's no air resistance and if there is no frictional force between the tube and the water, it would come back up to the height of the top of the dam. It doesn't do that because we're making approximations that aren't real. Okay, clicker question number 1. Oh, really? The connection to the response-ware server has been lost. Yeah.
Sabotage.
Let me start over again because I don't want people to get zeros. Click to connect. Okay, now you can answer. Sorry about that. What is the pressure of the water when it exits the hole in the dam? Okay, Christian, good. Okay. All right, Peter. There we go. So the answers we got had some variation. Now I'm going to do this a little different than I often do. I am going to have Irving say why. Well, I'm going to ask you the easiest question of all, Irving. We had one person that said 0 a vacuum. That was incorrect. Why was that incorrect?
The vacuum, it would have been the opposite direction, the negative pressure.
What does a vacuum mean?
Is that there's no molecules in it.
No molecules there at all, so no pressure. That's the lowest you can go, is to no pressure. So no molecules at all. Are there no molecules outside of the hole? No, there are molecules there. So that can't be it. Trace. Now we'll go to the correct answer.
I think it was C,
Okay, Trace chose C, and why'd you choose C?
because the opening at the bottom is just atmospheric pressure, so there's no difference.
Right. So I wanted to make sure we can contrast those two. You're open to atmosphere, so it's atmospheric pressure. It can't be vacuum, because vacuum would be no molecules there. Okay, a similar problem here. A fire truck needs to supply water with a nozzle gauge pressure 50 pounds per square inch, which I put it in Pascal so we can do a problem. If the nozzle is 10 meters above the fire truck, what must the gauge pressure be at the truck? Assume no pressure loss due to friction, which is a very poor assumption. As when you go to fire academy, you have, well, actually, you go to fire academy, you learn to be a firefighter, was it, I don't know, 1 or 2. All you know how to do is lob water on a fire and, don't die. Here's your, yeah. But when you become the engineer, you have to learn these things, and they actually have a calculation for the pressure. They use physics. But, these guys aren't taking a physics class. All they have is an equation that says, how many feet of hose do I have? I have to add this much pressure per foot of hose. What's the elevation change? I have to add this much pressure for the elevation change. But they have to be able to do those calculations. Otherwise, the guy's sitting there, there's a fire, it's really hot, and I'm getting a little dribble out of my hose. That's a dangerous situation. Or conversely, you can put too much pressure in the hose and pop the hoses, which is not a good thing either. So how would we solve a problem like this? What would your approach be? Pretend it's on the test. What would you write for concept? I've got 2 pieces to my concept, which is surprisingly the 2 things we've talked about in fluids. Okay, we're going to have to use the Bernoulli equation. And then I have another one. What's the one other thing that we've talked about in fluids? I think I might have heard Irving say the continuity relation. Is that what you said? Yes, it was. Good. the continuity relation. We have a hose, water goes on one end, comes out the other. If water is not being stored somewhere, we're going to have the flow rate the same going in as coming out. It stays the same area. So the continuity relation, because it stays the same area, is going to say V1 equals V2. Right? Because area 1 V1 is equal to area 2 V2. But if area 1 and area 2 are the same, then V1 is V2. So we have that relationship. And then we have the Bernoulli equation, which we just came here and we said, oh, we're going to have the same pressure and find out what the speed difference is. Now we're going to have the same speed, and we're going to have to find out what the pressure difference has to be for the heights. And so you go through and you do this, and it turns out to be real simple. So you have, let's do it right, pressure 2 minus pressure 1 is equal to 1/2 rho V1 squared minus 1/2 rho V2 squared. And I said V1 is V2, so those two add up to 0. Plus rho G H1 minus rho G H2. And so those come to 0. And I have my pressure differences, rho G H1 minus H2. And you're like, wait a minute, we did have that before. That's just the equation for the pressure difference in still fluid. This is now moving fluid, but we still have that relationship. And so, for the firefighters, they just have a factor of what density of water times G is. And they use that to calculate how much height they're going to need. So now we could put in the values necessary. What must the gauge pressure be at the truck? Well, if the gauge pressure is 3.5 times 10 to the 5th pascals at the nozzle, it's going to be 3.5 times 10 to the 5th pascals plus rho GH, where rho is 10 to the 3rd kilograms per meter cubed, and H in this case was 10 meters. So that's 10 to the 4th pascals. So 3.9 times 10 to the 5th pascals total. It's, wait, 3.9? I did that calculation wrong. 3.6 times 10 to the 5th pascals. So not a hard calculation. Now, just a funny real situation that occurred in Napa Valley. We've got this road that runs up the valley, and then beside the road, there is a canyon and a hill. Canyon's not very big, maybe 100 feet down. You shouldn't call it canyon. There was a fire burning up here. And so they had to run fire hose from the road down here up to here. And so the engineer says, okay, we've got this vertical distance of H, and we've got this much length of hose. This is the pressure I need. Irving's shaking his head. Why?
Pressure out in the hose is going to make it get out of the valve.
Okay, what's going to happen to the pressure right here? No, it doesn't kink. You got to be careful on that. But you come down, what's happening to the pressure? It's going up. And so while he had a safe pressure at the pump, the pressure down there at the bottom of the little ravine was higher than the ultimate strength of the fire hoses, and they just started popping fire hoses. And you don't put out the fire when you're popping your fire hoses, right? So that's something they didn't cover apparently in the engineering. I don't know. I suppose you would have to go ahead and put a platform of some kind to avoid that problem. So it was a funny situation. Okay, getting into fluid flow. This picture is showing smoke. Smoke rising, initially it's rising nice and smoothly. We call that laminar flow. It's flowing as layers. But as it rises, now, why does smoke rise? We haven't gotten to all of the ins and outs yet, but it's very simple. Temperature is a measurement proportional to the average kinetic energy of the molecules. So when something has a higher temperature, like fire, that means the molecules are moving faster. if the molecules are moving faster, they're bouncing off of each other harder, and so they expand. Hence, your whole ideal gas law, PV equals nRT, comes largely from that effect. So you raise the temperature, they're traveling faster, they expand, they're less dense, and what happens to less dense gas? It floats. And so because it's less dense, it has a net upward force, buoyant force, floats up, and as it goes up, it gains speed. It finally gets fast enough that you have a transition from a smooth laminar flow to a turbulent flow. And at the end of the lecture, we'll have the way we can determine if it's going to be laminar or turbulent. And so up here, you're seeing the turbulent flow. You see it doing funny things, right? You see all those funny paths it's taking. It's not going in a smooth flow. So we want to understand that a little better. What causes it is the fact that we have some kind of force between molecules in the fluid. So I called it here, actually this came from the textbook. The textbook calls it a frictional force. So we treat the fluid as a bunch of layers flowing one on top of the other with a certain amount of frictional force between each layer. If that frictional force is small, it just drags. But if the frictional force gets too big, then you'll have the fluid gets disrupted. It gets pulled back and can't flow. And so that's what causes the transition between the laminar flow and the turbulent flow, is the speed difference is too big between the layers that the frictional force causes it to not slide. So a quick definition. What does laminar flow mean? Becky, Jeffrey, James, Leslie. James, Jeffrey, Becky. Okay, everyone's answered. Excellent. We have only two answers, 19 and 7. Erika, which one did you choose and why?
I chose A because, like, as you can see, like, they're all going in pretty much the same direction, but like it's like different layers, as shown in the picture previously.
And what would you say to one of your friends who said uniform flow?
I'd say you have close to the right idea, but like it's layers.
Okay, it is close to the right idea because the laminar flow is nice and smooth flow. But the reason uniform is technically not correct is because you have different speeds in the laminar flow, so it's not perfectly uniform, right? But it's easy to see how 7 people answered that, right? It's not an unreasonable answer, it's just not perfectly correct. So viscosity is the term we use to talk about the frictional force between the layers. So this picture here is trying to illustrate how viscosity is measured. You have a plate down here at the bottom that's fixed, and a plate up here at the top that's moving at speed v. And capital L is the distance perpendicular or normal to the faces of those plates between them. And then you measure how much force is necessary to keep that top plate moving at speed v. And the viscosity, the thickness of the fluid, is the force necessary to keep it moving at a constant speed times the separation between the plates divided by the difference in speed of the two plates times the area of the plates. So the higher the viscosity, the more drag you're going to have. So you can think about that and put some reason to what viscosity means. Now, many of us have dealt with viscosity and not even known it. How many people have ever had to put motor oil or select motor oil for their car? Okay, that's at least half the class. So when you go to select motor oil and they say, what kind of oil do you want? How do you respond? And don't say whatever it says in the owner's manual. I mean, if you have some more knowledge than just whatever it says in the owner's manual. Because whatever it says in the owner's manual is a good answer. How do you respond if you're going to be more specific? Okay, Irving, say it louder.
5W.
Okay, so Irving says 5W30. What in the world does 5W30 mean?
Like the weight
It's the weight. Okay,
and the viscosity.
the weight is the viscosity, yes. When they say the weight of the oil, they mean the viscosity. Now, 5W30 is a little special. Back in the day, and this is probably before I was born, you would just get 30 weight. And what that meant was the viscosity in some random units was 30. If you got 20 weight instead of 30, what would that mean about the motor oil? It's thinner, it flows easier. 40 weight would be thicker, more like molasses. Now the 5W30, that's a multi-grade? I don't know what they call it. What that means is when it's cold, it behaves like a 5 viscosity. And when it's warm, it behaves like a 30 viscosity. Why would that be important? Why do you put oil in your car to begin with? I know some people, well, because the owner's manual says to. I don't know. But some people know. Why do you put an oil in your car? Lubrication, you don't want metal to grind on metal. In your car, you have things like, the bearings on the or the crankshaft. The bearings on the crankshaft are just pieces of stainless steel on another piece of stainless steel rod. So stainless steel on stainless steel. If you don't put something in between there, the steel is really going to tear itself apart. So the idea is to have a fluid in between there so stainless steel never touches stainless steel. You have that layer of fluid. Well, if the fluid's thin, it'll easily flow in there, but it's also easily squished out. If it's thicker, it's hard to get it in, but it's also hard to get it out. So the idea is when you start up your car when it's cold, you want that fluid to get in there really quickly, so you don't have metal grinding on metal for very long when you start the car. But then once the car is running and warms up, you want it to thicken a little so it doesn't get squished out easily. So that's why we have the multi-grade motor oils. Examples of viscosity and laminar flow. If you have a viscosity of 0, when you have something flow through a pipe, it'll just flow at the same speed everywhere through the pipe. That's not what you expect. You expect if you have a stream, the water is going to be relatively slow at the shore compared to if you jump into the middle, because you have the friction between the ground and the water at the shore. Whereas in the middle of the stream, you don't have that. You just have water on water. And so what you expect with a viscous flow is what's shown on the right here. With the speed fastest to the center and slower as you go out to the edge. These are both laminar flows, but only the non-viscous is, uniform. If you're making a fountain, one of the goals of a fountain is to have the water not come apart. If you have a flow profile like this, where it's going fastest in the center and slower on the outside, as the water flows, that's what happens when you have a hose, right? Water comes out of the hose. As the water flows out of the hose, it starts to break apart because the outer water is not going as fast as the center water. And so it pulls apart. So if you want to make a fountain that doesn't have the water come apart, you want to have something that is like this, which we actually call superlaminar. And how do you make that happen? Has anyone here ever actually gone to fire academy or done anything with firefighting? No. Well, in our nozzles, we have a thing that looks like this. And the reason for that is then you force the water through these and you're going to have friction on each edge. And so it makes it so you have this kind of profile in each one of those little grids. But if each one of the grids has the same kind of profile, when you put them together, your average speed is going to be the same. And so it gets you closer to a superlaminar flow. Your stream of water will stay together better. And so if you're making a fountain, of course, they want to do a better job than you do with the fire hose. They do things like they get a whole bunch of straws of certain length and pack them together to get a better superlaminar flow. And then they'll also try to put in some things maybe to make so it has stronger surface tension. Okay, getting to the end here. Poiseuille's law. Poiseuille's, the PHYS is the unit for viscosity, named after Poiseuille. We haven't talked about the unit of viscosity. You could go back to that equation, force times length divided by speed times area. You have Newton meters on top and meters cubed per second on bottom. You can go through and calculate what a Poiseuille or a PHYS is. But Poiseuille's law is the one that brings up what Amanda was talking about. The pressure necessary, or the pressure loss, when you have fluid going through a tube. Now, this is specific to a tube, right? A circular, cylindrical tube. Circular, cylindrical, sorry about that. A cylindrical tube will work. So the flow rate Q is equal to the pressure difference divided by the radius. Nope, not the radius. That R is a different factor. That R is this, which I believe we called the Reynolds number. 8 times the viscosity times, that's not going to be the Reynolds number. 8 times the viscosity times the length of the tube divided by pi times the radius of the tube to the 4th power. So R is a pretty complicated thing. Or putting in the value of R, the flow rate is the pressure difference times pi r to the 4th over 8 viscosity L. Or the final form that I put in light blue, pressure difference times the area of the tube squared divided by 8 times the viscosity times the length times pi. You had a question, Ashley?
Will it always be like the capital R? How can we differentiate that from the radius?
Okay, this is a really good question. There's only 26 letters in the alphabet. We also use some Greek letters. If you go to old school physics tests, they've used a lot more Greek letters and stuff to try to keep things separate. But you have to know the context of the variable to differentiate it. Because R can be resistance, it can be radius, it can be this here. You have to know what the context is to know which one it is. It's always a little discouraging on tests when you see somebody randomly choose an equation because it has the right symbol but meaning the wrong thing, so it's completely out of place. So why is this important? Well, as I talked about for firefighters, they simply have a calculation. If I have this length of hose, I'm going to need this much more pressure. And you can see how that's going to work because you have the flow rate, of course, is what you're looking for. Well, flow rate and pressure, and there's the length right there. So the pressure is proportional to the length if you solve for pressure difference. Or this is the case of my father. About 15 years or 16 years ago, he suddenly developed an occlusion in his coronary arteries. And he had a 90% occlusion in 4 coronary arteries. And so that means he had blockage in that artery. And so assuming you have the same pressure difference between the non-occluded and the occluded artery, I've now brought it forward so you can answer. So assuming Q is the same for, not Q is the same, the flow rate's the same, Q is the flow rate. The pressure difference is the same. Assuming P2 minus P1 is the same for both my dad before he had this and after he had it, how is the flow rate going to compare? So everything is the same here in that box is our assumption. Okay. Noah, Becky, Irving, Ed, I guess Jeff. Okay, now just Jeff. All right. Had to make sure Jeff got in because he was out of the classroom for the first one. This made the difference in his grade for the day. Okay, we had quite a mixture here. Normally I would have you discuss this, but since we're out of time, since the flow rate is proportional to area squared, it has 90% blocks, so the area is 10%. And if I square those, .1 squared is 0.01. Only 1% of the initial flow rate, which isn't very good now, is it? Okay, have a great day. I'll see you for last.